let's get started. So we left off where we talked about noise and the fact that we have to accept some of the noise that's present in the data, and there's nothing much we can do without at least investing a lot of time and money to get rid of it. And then there are some noise that you can't get rid of, for example, personal bias, where each person can have their own preferences. And there's always people like Anupam who like to watch the world burn, so we can't do much about it either. Now we move into the next phase of the entire full stack NLP procedure. We covered collection of data, cleaning of data, splitting of data into train, validation, and test. These are crucial parts. The next, what we did was talk about some of the aspects of the data we have collected, so that our expectations are in check. And now we get to the interesting part where we start building models. Now, in the previous session, Rebecca was talking about naive-based models and how they can be used in NLP. We're going to take the same approach. We're going to use naive-based classifiers. You're going to see two variants of it. And you'll see how we will then discuss how we can use them in production in a very simple setup. Alright. So the first problem that you have to realize is that when we're talking about models, we need statistical or machine learning models. Now, all models in mathematics need a numeric representation, and the better the representation, better is the quality of your model. So there are many ways to represent text these days, especially now. It's very exciting. People are coming up with very interesting ways to represent text. But the process that we're going to talk about here is more fundamental. It was developed a couple of decades ago, and it still works. I mean, I got a validation from Shai that he is performing pretty well with this representation that he's seeing. Yeah, he just cloned the repo and changed the data, and he's in the 5th position in the leaderboard somewhere. Anyway, so this still works, but it's not state of the art, and you can definitely improve on it. So we're going to represent documents as a bag of words. We don't care about the order of the words. We can bring the notion of order later into this scenario, but right now we don't care about the order of the words. Take a text document and we figure out what are the words present there. We can choose to ignore punctuation, or we can keep them. Ideally, for something like this, you can ignore punctuation. You can also, just so that capital "the" is not confused with small "the", we can make everything lowercase. That's a problem with some European languages, but for English it should work fine. Okay. So let's say you have 3 documents, and you can read them. I think it's pretty visible. So the first one is I love the pizza. The second document says the pizza is pretty nice. Also love the ambiance. And the third one says nice ambiance, nice pizza. So how do we represent them in a bag of words? So we take all the documents, collect all the words they have, and they become the column of a matrix. And for each document, we put a 1 if a word is present there. So in the column of I love the pizza document, all have 1s, and for the rest, it's filled with 0s. And you can see in doc 2 and doc 3, they follow the same strategy, where if a word is present in the document, they will have a 1 and otherwise a 0. So this is called the binary term document matrix. There are other forms of term document matrix, but let's work with this one for now. So now each document can be represented as a vector. As you can see, each row becomes a document, so that's a vector if you take out the row. Yeah?
So we make these documents.
What?
These documents, we make them.
So the documents in this case would be the reviews that we collected, and you can easily find out the words that are present there. So if you have a collection of all the reviews, you pick up all the words from them, they become your columns. And for each document, you see that which are the words present in that document, and you put a 1 in that column and 0s for the rest.
Manually.
I mean, there are pragmatic ways to do that. Well, no, we don't do that. No, we don't take ages.
Just one thing. So if, the documents are like big paragraphs. So in that case, what do we do?
So you take a paragraph and you take all the words. You don't care about the order of the words. You find out all the words that you have there. Now for each of the words, you put a 1. Okay, and for each of the, I mean, in other cases, they're already filled with zeros. So you have start with the 0 vector, and if a word is present, you go to that column that you see here. We see each of the column and put a 1. Now, if it was document 1, then you would represent as that vector that you see the row. So it's a couple of 1s and 0s. So it's a Boolean array. Okay, does that make sense? So now for each document, you actually have a vector of 0s and 1s. And that's how we're going to use it from here on. Does that make sense? So so for each document, we have a row, and for n documents, we'll have n rows. And so this entire thing is called a term document matrix because of historical reasons. There are other things that you can do with this thing, but for now, we're just going to focus on predicting sentiment. Okay, so how do we do that? Now, with every data science project that you undertake, do not just blindly plug in something and see if it works out. I mean, that usually how people get started, but when you're talking about things in production, it has to make sense. There should be mathematical standing behind it, and it also has to be efficient. You can't just build a very complex model that costs you thousands of dollars to make predictions. So let's talk about a very simple model, which was already discussed by Rebecca. So I will not give you a very detailed explanation of it, but we'll surely go through the basic concepts. So we're going to use something called the Bernoulli naive classifier. So anyone who knows about the Bernoulli distribution, it means it actually tries to model a coin toss. So if you say heads is true and tails is false, then the distribution, if you make n coin tosses, the distribution that if you plot all the heads and tails, the distribution that you should end up with is the Bernoulli distribution. The Bernoulli distribution is given at the end of the slide, but let's talk about the Bayes assumption before. So the Bayes rule means the conditional probability of, given that, let's say we only use the word nice. So we say that nice, if nice is present in a document, then nice is true. So it has a 1 in that. Okay, and let's say we only, so instead of this huge matrix, with all these columns, we have a single column, the nice column, okay? And we don't consider any other of the words. So how can we use nice to predict if a class is positive or negative? So if you just model according to that, it becomes pretty easy. The probability that a class is positive, given that the nice word exists, which is depicted as nice equals to true, is the probability of nice exists given class is positive multiplied by something called the prior, that is the probability of the class itself. So in our case, we saw that there's a lot of positive reviews and a lot of negative reviews. So the probability of a review being positive itself is pretty high, and that's where the prior comes in. The prior is the probability of a class being something. So in this case, the probability of a class is, let's say, 60%, so we'll just plug in 0.6 there. And then was the probability of nice being true. So in this case, if you just look at the column of nice, out of 3, in 2 cases, nice is true, and this one case was nice is false. So it's 2 by 3. So we actually can compute both the prior and the evidence in this equation. The problem is with the likelihood. And how do we do that? We go back in this matrix. The label is missing because this is just the document representation, but let's see if we also have the labels. In this case, they would all be positive because all of these are positive sentences. Then we try to compute in the cases where nice is equals to 1. So in the cases of dog 2 and dog 3, what's the label? And that is the likelihood that you're seeing here. In a more general format, you would not only want to condition on nice itself, not a single word, but all the words that you see here. And then the representation in mathematical terms becomes a bit more complex. Then we are conditioning on the joint probability, the joint case of class equals to, nice equals to true, and pretty equals to true, is equals to true, and also the negations. So I mean, let's not deal with the mathematics here, but I mean, it can easily be computed. If you put your mind to it, it's very easy to compute that for a Bernoulli based classifier. And the last part, where you have a lot of words that you take into account, you have to modify the likelihood function. Over here, it's just a simple probability where we talk about nice, but for multiple ones, you have to use the Bernoulli distributions. So the way you would want to think about it is the probability of, let's take document 2. So document 2 would be the probability of getting loved equals to true, pizza equals to true, thou equals to true, and blah blah blah, when the class is 1. So that's the likelihood. And the way you model is using this equation here. This is the Bernoulli equation. So if P is the probability of getting a true, then 1 minus P is obviously the probability of getting a false, and that's why it's also negated by 1 minus 6, raised to the power of 1 minus 6. So that's our likelihood function, and that's how we just plug it in this equation here. We plug this equation in over here, and we come up with a classifier that can predict the probability, that gives us the probability of the label being a certain class, considering all of x1, x2, x3, all the words that we have in our vocabulary. Okay. So let's do that. Let's see how we can represent that in code, and we'll get back to the next part of the model building phase. Alright, so in order to represent the documents as a term document matrix of zeros and one, we'll use this count vectorizer. This will read the document for you and convert it into vectors. So yeah, it is not manual, you use a function to do that. The class has the function implemented inside of it. We'll talk about matrix later. Yeah, we also import the Bernoulli based class from sklearn. Yeah, so let's get on with it. So as I said, we only deal with the train and validation set. So we read both of them in. And this is a small function that I wrote to remove digits from the text. I found that this reduces the feature space and also improves upon the precision a bit, but not a lot. You can choose to ignore this if you want. And so we apply this function here. So all the text that you see here will have no digits in it. Okay, so that's how we do the bag of words representation. We have the count vectorizer. Now let's look at the settings. We don't use any stop words. So stop words means the very frequent words in English like the, and, or, is. And we can, if we set this to true, then it will drop all of them. So if we set stop words equals to English, then it will not consider them. They're considered as noise, but personally I found that keeping them gives you a boost in this mode. Okay, but we do lowercase the letters, so capitalization doesn't cause another column to appear in the term document matrix. Capital, the with capital T and small t essentially means the same thing, so we lowercase everything. There's also something called n-gram. I don't want to discuss this in details right now, but n-gram just means that are you considering a single word as a column, or 2 words as a column, or 3 words as a column? When I say 1, 1, it just means 1 word as a column. N-grams help you capture a bit of order information in the term document matrix. In case of information retrieval, they come in really handy. Okay, this parameter is just a bit more important, min df equals to 2. It means ignore all words that do not appear at least 2 times in 2 different documents. Okay, so if a word only occurs in one document, we're not really learning much from it. So it should at least operate in 2 documents so that we know that's a valid word and we can use it as a reliable feature. And we also set binary equals to true so that we end up with zeros and ones. And then we have the traditional fit transform features so we get the train features from this vectorizer. So now train features is a sparse matrix of zeros and ones. And the train labels, we already have them. Same thing, we do the same for validation. And then we start with the Bernoulli model. So when we initiate this class, Bernoulli NB, we set fit prior equals to true. Now why is that? Why do we want to fit the prior? Because as we saw that there is a class imbalance and we need to capture that. So if you blindly look at any review and someone asks you what's the sentiment of the review, even without reading the text, you can say that it's a positive because we have more positive reviews than negative reviews. So the probability of finding positive review is higher. And that's why I said the prior, the fit prior was true. If I set it to false, then it will consider each of the classes to be equally probable. And that's something you would want to avoid in certain cases. In certain cases, you would want that to happen. For example, you know there is a balanced class from the test data you will be receiving, but the training set unfortunately doesn't capture that balance. So then you would set fit prior equals to false. Okay, then we use the fit method to train them, and then we do a model.predict to get the predictions, and we get a classification report. Now we're going to get into the details of these precision recall and F1 score, but let's focus on F1 score, and higher the F1 score, the better we are. And we'll see that the F1 score that we have, the micro average of the F1 score is 0.8. So we're doing pretty good, but we can definitely improve on top of it. Any questions?
Yes.
Yeah.
So when we are instantiating the count vectorizer,
Yeah.
So you set the stop words to none. So if I set it to true, does it mean that I have the list of all the words as columns, and then from that list I am removing some of the columns which actually are stop words?
So you can set stop words equals to English, and that will make sure that none of the columns is a stop word.
Okay.
So if there's a column like da, is, and, they would be removed.
Okay.
You can, it's standard practice to use it, but for this specific case, I saw there's a performance improvement if we do remove them.
And what about the binary is equal to true?
This is because count vectorizer actually counts the occurrences of the words. So we put binary equals to true, it truncates the counts to 1. So if it's 0, it's 0. If it's something other than 0, then it's 1, not the exact count. Any other questions? Used our intuition and skills to build a model. We should always ask ourselves that can we do better? Can we beat this benchmark? So usually when you first build a model, no matter how powerful it is usually can be improved a lot. Okay. So let's consider this as a benchmark and try to improve this model. So what's the next best thing that we can do? The next thing that we can do is, instead of saying that a word either appears or doesn't appear in a document, we can also say how much a word appears in a dataset. So let's look at the example that we have here. So if we look at document 3, it has nice mentioned twice in it, but we only have a 1 in this column. Now, when someone says nice ambience, nice pizza, he's actually stressing on the fact that he has a very nice experience there, right? But we don't capture the intensity. We only capture that, okay, the experience was good, but how good was it? So that's more information that we can have, and that's how we can change the representation. So you'll see that in machine learning or data science in general, the better the representation, the more information that you put into the initial representation, better is the quality of the model. We'll usually see that even simpler models will outperform complex models just because you're using better representation. So we use a count-based term document matrix where we just don't consider if a word is present or not. We also take in account the count. So in document 2, you'll see this thou mentioned twice, which is not informative in this case, but you also see that nice is mentioned twice, which is very informative. Okay, so we know that this guy had a very nice experience, and we can use that information. But this also changes the mathematics that we're using so far. So Bernoulli trials is modeling essentially head or tails, positive or negative. Okay, or not positive, negative, or if a word is present or not present. Okay, and we're doing it with a lot of words. That's given. But if we are considering counts, then the definition changes. It says how many heads are we getting and how many tails are we getting, or rather than that, how many times nice occurs, how many times pretty occurs, and all those stuff. And when we're modeling counts, we can't rely on Bernoulli distribution anymore. We have to move into count-based distribution. And the most simplest count-based distribution is a multinomial distribution. We all have done binomial expansion in high school, and multinomial is just, so binomial expansion was when we use two variables a and b, and we raise it to the power of something, and then we expand on top of it. Multinomial means we just do not raise it to raise a and b to the power of something. We also consider n number of variables. So we have a, b, c, d, e, f, and we a plus b plus c plus d plus e plus f, and we raise it to the power of something. Now, this is a multinomial expansion, and in the same case, when we're considering counts, we can also have a multinomial distribution, where each word has a likeliness based on the count. So that's the way you think about this is that what's the probability given the class, given nice occurs 5 times, the class is positive. Okay, now this, you can see from the definition itself has more information than what we were considering previously. And we use the same base formula to represent this, and we can, so on the right hand side of the equation you can see all the things that we can compute on our own, but this is only considering the fact that we're using nice as the only feature. If we consider all the features, then we have to use the likelihood, we have to change the likelihood function, which is given here. So yeah, the fact that we're using the multinomial distribution means that we're by default dealing with counts. If anyone is wondering, the exclamation marks that you see over there, they are representing factorial, so you can see the pretty large numbers we're talking about. So that's the summation of all the x's, and then we take the factorial of that. So, and this is the product of a lot of factorials in the denominator. So this doesn't only tell you how we can get a combination of words in a document, we can also say that what is the, not only the combination, but we also can say that what is the frequency of each of the words, and model that exactly using the multinomial distribution. Okay, so once we have that, we can incorporate that into code and see how we can improve the model or not. So mind you, right now we have a macro average of the inference score to be 80%. So we change our representation, everything remains the same except for the fact that we do not have binary equals to true in this case. So now we are dealing with raw counts instead of binary, and we do the same transformation, and now we use the multinomial model, and yeah, do the same thing, get a classification report, and you see that it has improved not by a lot, but just by a bit. We have 81% macro average inference score. If you go back, you see that the micro average is also 81, which is also improved. The most important part is the recall, and you will see that the recall has decreased a bit for the negative class, but increased quite a bit for the positive class. So from 84%, it has gone up to 87%. Okay. So we're already doing better, and if you just look at the accuracy, we're also doing better in terms of that, 81 to 82%. Yeah. So we have a better model, and we use very basic intuition to come up with this. The next step would be to analyze the performance on the test set. Because when you are optimizing on the scores on the validation set, there is this human intelligence that you're applying on your model. You might be tuning the parameters so much that you're overfitting on the validation set. You are making the model more closer to the validation set rather than the original distribution, and you need to remove that bias. The way you do it is you apply the same model on the test set and see if it's near about the same kind of scores that you're getting. So we do that. We load up the test set, apply the same transformations, and we compute the metrics, and we see that the macro is not that good. It's 78%. But I tried out playing around, and that's the best you can do given the training set that we have. Okay, nothing much to do there, but we're still good in terms of accuracy. So let's just say 80% of the time your model will be able to predict if a review is positive or negative. Alright, so since we are reaching the final stages of the model building, we would also want to incorporate the validation data into our training data. So instead of just taking the training data into account, we concatenate the validation data along with the training data. And so that way we have a larger training set to train on. So we do that, we concatenate training and validation here. And we do the same multinomial model here, multinomial height-based model here. And yeah, we come up with the newest scores, which is not that much of an improvement, but we know now that the model has been trained on more data, so it will generalize better to more incoming data. And then we use something called Escalon's joblet. This allows you to save the model that you trained into a binary file, because we are also focusing on production. And in production, you don't want to train it again, right? You just want to load up the model somewhere and start making inferences on it immediately. So that's how pipeline and joblet helps you. We not only save the model, but we also save the feature vectorizer, so that now if every text comes in, it automatically gets translated into rows of zeros, rows of counts, word counts, and we pass that into the model. And there's a very simple code that lets you do that. It's just joblet.dump, and it dumps the model as a binary file. If you load it back up, you will see that every single operation that you were doing on top of the data has been condensed and kept over here. All good so far? Any questions?
Yeah.
Yeah.
What is the difference between saving the model via direct pickle and this job link?
So I think it's more convenient because now you can just do a joblet.dump model, but if you save direct pickle, you have to also mention the file with, open a file, then give the location, and this is most convenient, just one line of code, which is just convenience.
We are here mentioning the pipeline also. They are direct the object basically.
So the pipeline lets you apply one transformation after other. We don't directly put the text inside the classifier, we convert it into a count vector before we do that. So this lets you do that at one go. It first passes it through the vectorizer. The vectorizer output then goes into the classifier, and from the classifier you get the prediction directly. So this is a condensed way of doing a couple of steps. So if we had more steps in between, we could have all put them in the pipeline, and you'll get the output immediately without having to write down all the steps again. Because in production, you don't really care about the logic that went behind your model. You only care about loading up something and start making predictions. So the production should be agnostic of whatever you've done in the middle stages. Any questions?
Can you just explain one more time about the pipeline?
So the pipeline, so we have two parts of this model. The first part where we take a text and convert it into a feature vector, and the next part is passing the feature vector into a model to get predictions. So we can decide to keep them separate, or we can compress them into a single object. so that in the model, in the production, it's always the same code. You don't have to care about, if you add something else, you don't have to care about that in the production. The production code remains same. You only change everything in between and dump it as a single pipeline. So it has all the steps condensed into a single object. Yeah.
I have a question. Since you said that you are saving the model for the
Yes.
production, right?
Yeah.
So what kind of data ops you're using instead of DevOps? I'm not talking about DevOps. So
Okay.
since you're working on data science, you're
Yeah.
supposed to use some kind of data ops. So is there any data ops you have used?
So in this case, we are not going to discuss about how we can manage all these binary files. Binary files are very problematic in handling, but in industry it's common standard to dump it into a, let's say, Amazon bucket,
Okay.
and we write up a cron job that automatically reads when there's a new thing added there, so it automatically reads the model and keeps one in this one running while the other model is loaded, so there is no gap in between between this transition. Does that answer your question?
Is there any tool you're using? Or like DevOps, we are using like Azure or something for Microsoft.
Okay.
So is there any kind of tool you're using for this data ops? I mean,
Yeah. So you should ideally use queuing software for this, queue-based system. I think Kafka is one of the most popular ones, and there are a few more. I think both Azure and AWS have their own queuing mechanisms where this is done. But but that is really out of scope for this thing because this is very introductory. But yeah, you would ideally want to have a queuing mechanism implemented. So whatever infrastructure that you're using, if it offers you something. So yeah, we have saved the model, and now we can go into writing the code that will help us in production. Okay. So before we do that, let's also talk about the scores that we mentioned there. We talked about precision and recall, and I really didn't explain that in details. All right. So before moving into production, how do you know you're doing well on your data set? A couple of metrics that you can use. Accuracy, everyone knows about accuracy. It's like how many times you've got it right divided by the amount of samples that you have. But accuracy may not be the best choice in this case. And for this particular problem, you already have a lot of positive reviews. So if you just build a model that say any review is positive, you already have a 70% accuracy. And you don't want that. You want something better than that. So the next thing you would want to look into is precision. So precision means the amount of predictions, the amount of correct predictions that you've done, divided by the total number of predictions that were the total number of documents that were present. So it's the intersection between relevant documents and retrieved documents. So divided by the total number of retrieved documents. So if you look at the denominator, it depends upon what are the retrieved documents, so what are the predictions. So if I say given any review, we just say that all reviews are positive. So now then this becomes as bad as accuracy in our case, because if we say everything is positive, everything is positive, then we still have a 70% accuracy where our model has not learned anything essentially good. So the next thing that we should look into is recall. So if you look at the denominator in these two cases, the only thing that changes is the denominator. It's not divided by the total number of retrieved documents, but the total number of relevant documents. So this is the intersection of classes that were actually predicted to be positive divided by all the positive class examples that we have, the number of positive class examples we have. But you can see that if you try to increase precision, your recall could go down. And if you try to improve recall, your precision could go down. So there's always a trade-off between these two. And we need to come to an agreement between these two. So that's why we use something called the F1 score. So this is just the harmonic mean between precision and recall. And this is the formula for that.
Can you handle that part?
So when dealing with class imbalance, we should always think about the numbers that we're predicting. Do not just go by a single number. Come to a single number after you have carefully analyzed the scenario that you're in. Precision and recall need to be combined to an F1 score so that we don't lose out on any of them we want to. So recall is the ability of the model to recall something if a class existed or not. And precision is the model capacity to make predictions in a very accurate manner. So precision is class-wise, recall is also class-wise. In this case, we only have two classes, so we don't have to worry too much. But when you have dealing with multiple classes, this will turn out to be a problem. Okay, so let's look at how we can deploy this model. So we have our pickle file. All that remains is getting the data and loading it up, start my introductions. Anyone here who doesn't know what a REST API is? Okay, so for example, in this case, when you need to have a prediction for reviews, this is how we would want this to happen. There's something running somewhere in the server, and you want to make a request to the server sending a review text, and the response that you get back should be the sentiment. So this is vastly generalizing, but this is somewhat what is called a REST framework, where you send metadata, when you send the request, and the response is something done on top of the request that you have made so far. So there should be a server running the model that you've created, and to make queries using JSON, simple JSON structure, JSON objects, and you get back JSON objects in return. Okay, and we're going to build that. We're going to start a server in Python using a package called Flask, and that's all you need. All right. So the first thing that you should do, and if there's anyone who interested, he or she can code this up as we go. It's a pretty small script, and I'll be discussing every single line in details. So I would really suggest that you code this up in spite of the fact that it's present in the repo already. So the first 3 lines talk about the imports that we're making. So of course we need joblib to load the model that we've done before. From Flask, we'll need the Flask object to start the server, request to process the JSON request that we'll be getting, and JSONify to return the values that will be given back to the user. And we need strings for the function that we move the digits. So the first thing that we do is we create a Flask object and call it app. You can call it anything you want. So this essentially creates a nice, neatly packed bundle that lets you start a server from scratch in Python. Okay. Now with any server, you need a path. So for example, in Zomato, we had the zomato.com/Kolkata/VBQ parts rate. So this is the path of an exact page, and you would need the same thing for the REST API. You would need an exact path. So I chose the path/infer, means it's making inference, and it only accepts post methods. Anyone needs clarification on what a post method is? So when you are submitting a Google search, making a Google search, the way the data is sent is through a GET method. It's an HTML, it's a web terminology where GET methods are sent over the URL. So whatever you type, you can see in the URL itself. And when submitting forms that containing sensitive data, they are sent invisibly, and that's the method to do that would be the post method. So we'll be sending data via the post method. You can also choose to send data via GET method. It totally depends upon you. In this case, the data is not too sensitive. But ideally, people use post methods in most REST APIs. Okay, so it only accepts post requests. And so this is what we do. We load up the data from the dump that we have. We start the server at port 9000. You'll see that I've set debug equals to true. You can choose to ignore that, but this comes in handy when you are making changes. So any change that you make to any file, the server restarts on its own, tracks the changes, and restarts and reloads the model. So we first extract the text that we're sending. We remove the digits like we did before, and we get the prediction. You see that I put text inside a list, a Python list. This is because the model expects multiple documents, not a single one. So I mean, if I put it in a list, it will just make a prediction for a list containing a single document. And then the response is a dictionary, having the sentiment as key, and the prediction